when we look at taking electron configurations and making them shorter, we're looking at condensing them using a noble gas. Okay, and where are the noble gases found on the periodic table? Group what? Group 18. Okay, these are the group 18 elements like helium, neon, argon, krypton, radon, xenon. I have those two out of order, but those are our noble gases. Okay, and so what we do in an abbreviation is we say our electron configuration is the same as neon plus some extra, right? Or it's the same as krypton plus some extra. So why do you think it is that we can only abbreviate using a noble gas? Yeah, Hannah.
Because they have all the electrons they want.
That's right. They have full shells. So before we can move down a shell, we know that our noble gas has to, before we can move down a shell or before we can add another shell of electrons, we know everything has to be full up to that point. So when we reach our noble gases, they have full outer shells, which means their inner shells have to be full also. Okay, does that kind of make sense? So noble gases, we know, have 8 valence electrons. That's a full outer shell. So that means everything underneath that can be full as well, or has to be full as well. Okay? So let's do calcium first, the regular electron configuration of calcium. Regular electron configuration of calcium. Okay, calcium is found in what block? The 4s, right? So we're going to fill everything up until that 4s point. So if we check our electrons, 2 plus 2 is 4, plus 6 is 10, 12, 18, 20. Is our atomic number of calcium 20? Okay, so this is our full electron configuration for calcium. So what we can do is we can abbreviate with a noble gas. So we look at the noble gas in the row above calcium. Okay, so what is the noble gas that comes right before calcium? It's argon, right? Calcium's in the 4 group, so we look for the literally right above that in the periodic table, and its noble gas, which is argon. So this is how we abbreviate. We put it into brackets. Argon. Okay, so we're saying the electron configuration for calcium is the same up to argon, which is right here. Right? Would you agree that for argon we would stop at 3p6?
Yeah.
Okay, so anything that comes after that is how we finish it, 4s2. Okay, so this is the electron configuration for calcium as well. Okay, both of those things mean the same thing. One is the full version, one is the abbreviated version. Okay, so what this abbreviated version tells us is that our electron configuration looks exactly like argon plus this stuff, plus whatever follows. Okay, so our electrons are stored in calcium just like they are in argon, except now we've added this 4s shell. Okay, does that part make sense? So it's always the row above that in your periodic table. Okay, so even if we add in our lanthanides and actinides here, right, we would look at the row above them on the periodic table. So you don't need to worry about necessarily the shell right above them, right, third shell or fourth shell. We're just looking at literally on the periodic table what's the row right above that. Okay. Okay, let's find the abbreviated electron configuration of iron. So unless it specifically asks for the abbreviated, you do the full version. But when we ask for abbreviated, we can use that noble gas notation. Sometimes you'll hear the book say noble gas notation, or on CK12 it might ask for the noble gas configuration. That's the same thing. Okay. So what's the noble gas directly above iron? Right, in the row above iron. Still argon. Okay. So we put brackets around it. We say it's argon plus 4s2, 3d what? 6. That's it. Okay, so iron is number 26. So the way you can check yourselves in terms of counting electrons here is you look at your noble gas, right? Argon has 18 electrons. So you'd say 18 plus 2 plus 6 gives us 26, which is what we should have for iron. So you can still check yourself for your total number of electrons. You just look at how many argon has plus how many others we have labeled here. Okay, any questions about abbreviated?
So this will only have to do with...
You can, that's right, you can only abbreviate with noble gases. So we can't abbreviate iron with manganese, the one right in front of it, right? We don't say this, Mn3d6, right? That's not how it works. You can only abbreviate with the noble gases. Okay? Okay, why don't you try strontium on your own? Strontium, SR. Okay, and that's number 38. It's in group 2. Okay, try that one on your own.
Like, you know how there's not like every like element on this? Are these like the only ones that like...
All right, Grant, why don't you tell me what you had for tellurilium?
OKR in brackets, 5s2, 40, 10, 5p4.
Perfect.
Why do you put like the ones before?
This one right here? Oh, you mean not just the last thing right here?
Yeah.
Okay, so we're the same up to krypton, which only goes through 4p6. So if you were doing your full electron configuration, after 4p6 would come 5s2, 4d10, 5p6. So we say it's the same up to krypton, and then everything after this is the rest of our electrons for tellurilium. Okay, good question. So we can't leave off everything besides 5p, right? We got to put anything after krypton to get to tellurilium. Okay? Any other questions with abbreviating? Okay. We're going to look at representing our electrons in kind of a visual form now, right? We wrote out electron configurations using 1s, 2s, 3s. Now we're going to draw our individual electrons using something called an orbital diagram, okay, or an orbital notation. So if I ask you for electron configuration, that means 1s2, 2s2, 2p6, whatever, okay? Orbital notation now is drawing out the actual electrons using arrows, okay, and I'll show you kind of what that looks like, okay? We're going to draw our orbitals out using lines or boxes. Sometimes you'll see boxes, sometimes you'll see circles, which represent individual orbitals. So an orbital that doesn't have any electrons in it, or it's an unoccupied, it's just an empty line. If I have one electron, I represent it with one arrow, or if I have two electrons in an orbital, I have one arrow going up and one arrow going down. Okay, and we'll talk a little bit more about why that is the case here in a second. And realistically, when you draw electrons, it's kind of a half arrow like this. Okay, but I couldn't do that in my software. So when you draw arrows, it doesn't really matter which way you go, but this is how I will draw them. Okay, and that's an electron. This is two electrons. Okay, and something that we need to look at in this diagram in terms of representing our electrons is that when we have one electron, what direction is it pointing? Up. Okay, and when we have two electrons, what direction are they pointing? One up, one down, right? This for this reason. Within an orbital, if we have two electrons, they have to have what we call opposite spins. So one is spinning one direction, one is spinning the other direction. Okay, so when we draw our electrons, we're saying this one has a positive spin and this one has a negative spin. Okay, the upward is the positive, the downward is the negative. You should get used to drawing always your positive spin first. Okay, positive spin needs to go first. The way we draw our diagrams, it looks really similar to our electron configuration. So we're still dealing with the 1s orbitals and the 2s orbitals, 2p orbitals, all that kind of stuff. But now we're drawing out our individual electrons. Okay? So let's look at a couple here. Okay, so there's a couple rules we need to follow when we start to deal and draw our orbital diagrams. Okay, the first rule, this is Hund's rule. The first one says orbitals of equal energy. These are things like 3p or 5d, right? Those whole orbitals of equal energy. These two are not equal to each other. I'm saying all the 3p orbitals are equal to each other, or all the 5d orbitals are equal to each other, and so on and so on and so on. Does that part make sense? Yes or no? Okay. They have to be occupied by one electron before any orbital is occupied by a second electron. Okay, so as we start looking at energies within orbitals, we said lowest energy orbitals are closest to the nucleus. So 1s orbitals have less energy than 2s orbitals, which have less energy than 2p orbitals, which have less energy than 3s orbitals. Do you see where I'm going with this? Okay, so as we move up on our pathway and on our periodic table and everything is like this, as we move forward in our orbitals, they are increasing in energy. So what we're saying is that the 1s orbitals have to be filled before we can move on to the 2s. And then the 2s orbitals have to be filled before we move on to the 2p. Okay? We talked about this before, but it's the same type of thing. Okay? So equal energy orbitals have to be filled by one electron before they can be filled by a double, and I'll show you what that means when we look at an example. All electrons in singly occupied orbitals must have the same spin state. So what this means is that when we start adding our electrons, we need to always add the positives before we go back and add negatives. Okay, must have the same spin state. Again, I think this will make sense when we look at an example, and I'll explain all these rules kind of in motion, but I want you to have them first. Okay. All electrons in singly occupied orbitals must have the same spin state. Okay, and we need to get used to drawing positive electrons first. Okay, which means positive spin, so with an upward arrow or half arrow, however you want to draw it. Okay, let's look at an orbital diagram for nitrogen. Okay, the first thing I want to do, we're going to connect our electron configuration with our orbital notation. So let's do electron configuration for nitrogen first, which means 1s2, 2s2, that kind of stuff. Okay? Nitrogen is found in the 2p block. So to get there, we say 1s2, 2s2, 2p3. So this is an electron configuration, right? We know how to do this. Electron configuration. Now the orbital notation or orbital diagram or whatever you want to call it is going to be right below, okay? We're going to draw out our orbitals using lines. This is our 1s orbital. Okay? And each orbital can only hold 2 electrons. So in my 1s orbital, how many lines do I need? Just one, right? The 1s can only hold 2 electrons, so I only need 1 line. 2s orbital, how many electrons can it hold? How many can the s orbitals always hold? 2. And since each line can hold 2 electrons, right, I'm okay with only 1 line. 2p, how many total electrons can the p orbitals hold? 6. And each orbital itself, each individual line can only hold 2 electrons. So how many lines do I need? 3. We said 6 electrons, each can hold 2. So here are my 2p orbitals. Okay, does that part make sense or not so much? Right, if we were looking at our shape of our orbitals, right, here would be one orbital, here would be the second, here would be the third, right? There are different orientations around the nucleus. And we're going to learn about all that here in a little bit, but that's what it would look like.
Do you have to write the 2p like in the middle?
Yeah, you should. You should. It's not going to, I mean, I'm not going to take you off right now for it, but you should just think about, yeah, these 3 orbitals all go with 2p. Okay? So let's fill our electrons. The first energy level is 1s. Okay, so I'm going to fill a positive 1 and then a negative 1 before I move on to the next one. Okay? My next is 2s, so I'm going to fill my positive, then my negative. Okay, so I filled 1s before I moved on to 2s. I filled 2s before I moved on to 2p. Okay, so that satisfies this part of Hund's rule. Okay? orbitals of equal energy, like the 1s, and the 1s has to be filled before I can move on to the next higher energy, which is 2s. Has to be filled before I move on to the next higher energy, which is 2p. Okay, so now we're going to look at the second rule. All electrons in singly occupied orbitals must have the same spin state. So we're going to work on both of these rules. Have to be occupied by one electron before moving on with a second. So I can't go 1, 2, 3. That's not how it works. Okay, I have to fill each orbital with 1 before I would go back and put in a second. That's what this is talking about. Orbitals of equal energy, which the 2p orbitals all have equal energy, must be occupied by one electron before it's occupied by a second. So I got to fill it 1 across first before I can go back. Do I need to add any more electrons? No, I don't need to, right? And for nitrogen, I don't need any more. If I did, if I was doing oxygen, then I would go back and I would occupy it with another one for fluorine, another one for neon. Okay, but nitrogen itself, here's what our orbital diagram looks like. Okay, what questions do we have?
So those are just half arrows.
Okay, and when it says all electrons in singly occupied orbitals must have the same spin state, that means that I can't go like this. Let's see if I can get back. I can't go 1, 2, 3. Right, that's no good because they don't all have the same spin state. They need to all be positive spins before I go back and add negatives. Okay, you want to try a couple more?
So why isn't there, since the 2p has 6, right?
It can hold 6, but how many does nitrogen use? Only 3. Okay, so it's only going to use 3 in that p orbital. It could hold 6. So if we were trying to do neon, we would fill all of those in. Okay, does that make sense?
Yeah.
Okay. All right, let's try boron. You don't have to write the electron configuration first. If that helps you, you're welcome to do that, but you do not have to. Okay. Tell me what block boron's last electron is found in. Right, what is boron found? Where's boron found? 2p. So that means that's where its last electron is. Right, it's in the 2p block. So I'm going to draw my orbitals. 1s, 2s, and 2p. Okay, so I'll fill my energy levels. The 1s has to be filled before I can move on to 2s. And now 2p, how many electrons are held in that 2p orbital for boron? Only 1, right? So can I put it on any of the lines? No. And can I put it positive or negative? No. Has to be going on the first line and has to be positive. Okay? Do I need to draw these other 2 lines even if they're empty? Yes, you do, right? Unoccupied orbitals within that energy level have to be drawn. So even though there's only 1 electron in 2p, we still have to draw these 2 orbitals to show that they're there. They just don't have any electrons. Okay?
So you said there's only like 1 electron left in like the 2p, right? So the other ones in 1s and 2s.
That's right. See how this is what it shows right here. The first 2 electrons for boron are in the 1s orbital.
So like 1, 2, 3, 4, 5. Is it like 5 is these ones?
That's right. That's right. So the arrows, we have 5 arrows, which means boron has 5 total electrons. 2 of them are in the 1s orbitals. The next 2 are in the 2s orbitals, and the last one is in the 2p. Okay, does it make sense?
Yeah.
This might be kind of stupid, but is all the s orbitals, do they all have the up and down arrow?
Yeah, they'll all have 1 up and 1 down, right? If an s orbital is full, if we were looking at, let's say, sodium, right? Find sodium. That only has 1 in there. So it would just have 1 positive electron.
So like in the D block, would you have 5 lines?
Very good. Let's try one, okay? So Grant asked if in the D block of orbitals, wouldn't we have to have 5 lines? That's correct, right? Because the D block can hold 10 electrons. So we would need 5 orbitals per. That's good. Let's try one of those. Okay. I don't want to do these practice ones. I want to do. Let's try nickel. Okay? Again, you don't have to write the electron configuration, but if that helps you, then do it. And then you can put it into a drawing of an orbital notation. Okay, something that I want us to think about as we fill these orbitals, and this is true for the p orbitals and any p orbitals, d orbitals, f orbitals, okay? Since we have to fill all of them with one electron before we go back and fill the second, you need to get used to filling them this way. 1, 2, 3, 4, 5, 6, 7, 8, right? We need to go all the way across before we come back and add a second. Okay, and that's true for the p orbital. So if you watched as I did that, I went 1, 2, 3, and then came back 4, 5, 6 for the p orbitals. Okay? For the d orbitals, you should not have had something look like this. Right? Because this guy's not full, and these have 2. Okay, so we have to make sure that we really focus on doing it the right way. So 1, 2, 3, 4, 5, 6, 7, 8. I think nickel has 8 in the d block. Would you agree? Okay. So if you know an orbital's full, like I get it, you can just put in, the 6 or whatever, but it's a good habit to make sure that as we were filling in, we went 1, 2, 3, 4, 5, 6. Okay? Do we all have nickel to come out looking like this? Yeah? So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. Good. We matched at 28 electrons. So you can still count your electrons to double check yourself. All right, how are we feeling? Okay? All right, good. We'll stop right there with new stuff.